Okay. So, that up to this point we have covered that sound transmission, sound reflection, and then sound wave propagation, that basic theory part. Now, we go for that application oriented part more right now. Okay. So, now we go for the acoustics environment. Acoustics environment. What happened if you switch on a, I switch on a sound source here. If I switch on this, this is the sound source. If I switch on the sound source, sound wave will be generated and it transmitted in a spherical in nature. Spherical wave transmission will be happen. Okay. So, I put on a microphone in a open field. What will happen? A loudspeaker in open field. So, a sound field will be generated and it will be travel along the field. Okay. So, it create an acoustics environment. Maybe there is no one single loudspeaker. So, I played a loudspeaker, somebody moving by a car, somebody walking and somebody making a noise. So, all kinds of sound source contribute to the acoustics environment. Okay. So, it creates an acoustic environment. Now, if I create a sound here, as per the inverse square law rule, that every doubling the distance from the source, the sound intensity will be dropped by 6 dB and sound pressure level will be dropped by 3 dB, because 1 by r square in case of intensity, pressure 1 by r. So, once I double the distance, the half power time 3 dB will be down. Okay. So, that means, in case of sound acoustics, when acoustics propagate in an environment, it supports the inverse square law. So, I can say some factors which affect the acoustic environment, which are, I have to know which are the factors which affect this acoustic environment. The factors are inverse square law. That means, if I produce a sound, if I doubling the distance, if I away from the sound, once I away from the going away from the sound source, every time I double the distance, my intensity will be dropped by 6 dB and power will be level, sound pressure level will be dropped by 3 dB. How it is done? You know that if it is power is P at R1, let us at R1 this point the power is P. So, it is sound pressure is P by R1. Now, once I got it R2, then it is P by R2. If R2 is equal to 2 R1, then it is nothing but a P by 2 R1. So, it is nothing but a pressure level is half of the reference point. So, if I say it is a reference point, then it is nothing but a reference point pressure level divided by 2. If I convert it into dB, that means that if the reference point pressure level is let us LR, then plus 20 log reference point distance dr, or you can say R1 divided by the R2 point distance R2. So, the power level at R2 is nothing but a reference point sound pressure level plus 20 log reference point measure distance divided by the measurement. So, it is the measurement point distance, For intensity, it will be same IR plus IR in dB plus 10 log, similarly R1 square divided by R2 square, or you can say that square will be removed. So, it is nothing but R1 by R2. Okay. So, R1 by R2, understand. So, in case of doubling the distance, intensity 6 dB and pressure level 3 dB. Okay. So, that is called inverse square law. Then, if I produce a sound in an open field, I observe that after certain distance, I cannot hurt the sound. It may be effect of the inverse square law. It may be effect of the attenuation due to atmospheric absorption. So, in atmosphere, there is a air. So, through the air sound is travelling. So, there is a atmospheric absorption is happened. So, due to the atmospheric absorption also sound will attenuated. Then there is a reflection and diffraction around the solid object. I create a sound, there may be a wall, there may be a inclined plane, there may be a sliding ground. So, from everywhere the sound will be reflected and refracted, that will create a problem, that will create that affect the sound acoustic environment. Then refraction and shadow formation by wind and temperature, there is a shadow formation by wind and temperature, I will discuss detail. And then reflection and absorbed by the ground surface, ground surface also reflects some energy and absorbs some energy. So, all kind of obstacle are contributing the acoustic environment. Let us we discuss one by one. One is called attenuation due to, so inverse square law you understand. Now, attenuation due to atmospheric absorption, attenuation due to atmospheric absorption. This is done due to the viscosity and heat conduction of the air medium. When a sound is travel, then due to the viscosity of the air and heat conduction of the air, we have assumed that medium is adiabatic, but there may be heat conduction happen that create a loss. So, there is a great deal of research on that, and they find out that it is absorbed, sound absorptivity will be increased if there is a viscosity and the heat conduction is increased. Okay. Then loss due to the relaxation behavior of vibrational state of the oxygen molecule in the air, which also depends on the humidity, absolute humidity. So, sound absorption, atmospheric absorption due to the atmospheric humidity also depend. So, if we see this following curve is a output of some research that how that humidity affect the sound absorption. Okay. So, this curve is given. So, I can say the atmosphere is nothing but an absorber. Okay. Next, very important part, that we said the velocity of sound depend only on the type of gas and the temperature and is independent of change in pressure. What is the meaning is that? That if an acoustic environment, the velocity of the sound depend on the type of gas and temperature of that medium, not the pressure. That means, if the velocity of the sound in Calcutta and if I measure the same velocity of the sound in Darjeeling, which is high altitude, the sound atmospheric pressure level is less, equilibrium pressure level is less, but sound speed will be same if the temperature and type of the air is same. So, in that two case sound speed will be same. So, this is the proof how the sound velocity of the sound only depends on temperature. If you see, velocity of the sound is only depends on temperature. Okay. So, if the temperature increases, the velocity of the sound is also increases. You just can see that, and it is a very small deduction. I have already discussed it in that previous class. Next, if that is happen, then there is a shadow formation due to the temperature variation. See these two pictures. One picture is that let us don't discuss about the case 1 and case 2. Let us first physical discuss what is physical. Suppose I create a sound in here and sound is traveling along this direction. Now, I said that there is a warmer, that means this portion air is warm and this upper portion air is cooler, like that kind of gradient is temperature gradient is happened. So, I can say that this along the ground it is warmer and above the ground it is cooler. Now, once this is one boundary. Once the sound is incident on this boundary with a angle of theta I, incident angle. Now, I said that if the temperature is high, velocity of the sound is high. So, if it is velocity of sound is C1 and velocity of sound is C2, since C1 is greater than C2, then I said the refracted wave will be towards the normal. So, this is theta t is less than theta I. We have already proved that. So, in that case the sound will be bent towards the normal. So, what will happen? The sound path will be look like this, bend upward. So, sound is want to go this straight line, but due to the temperature gradients it create a path like this way. So, if a person is standing in here, he cannot hear that sound, because that sound is not come in this direction, sound is already go upward. So, that is a shadow formation is happen. Okay. Similarly, if upper portion is warmer and lower portion is cooler, what will happen? This is the boundary, sound is incident on that boundary. So, this is the incident angle theta I. Now, C1 is less than C2. Okay. So, if C1 is less than C2 and theta I is less than the critical angle, then what will happen? Sound will be away from the normal, theta t is away from theta t is greater than theta I. So, it is away from the normal. So, if it is away from the normal, that means the sound will be bent downward. Okay. So, if that kind of lower portion is cooler, upper portion is warmer, then what will happen? Sound will bend downward. Okay. Now, you think about the phenomena. Sometime you say there is a loudspeaker is playing and there is a wind on the direction of the sound. We said that since the wind is in the direction of the same direction of the sound, that is why sound travel is long distance. Actually, that wind does not affect the sound velocity. Sound is affected due to the temperature gradients for the wind blowing. So, in the case of case 1, wind is blowing in the same direction of the sound, produce temperature gradient along the ground surface, and that tends to refract the sound downward. So, if a sound is coming from here, then it is going downward. Okay. For same direction, the direction of the wind is the same as the direction of the sound. Now, if the direction of the wind is different from the opposite direction of this direction of the wind is this and sound direction is like this, or the wind is following this direction, then what will happen? The sound will be refracted upward because of the temperature gradients. So, that is why sound cannot travel long distance, because it is going upward. So, this refraction and reflection effect will be. Then what is the reflection effect? Let us acoustic environment, I create a sound in this room. So, this sound will be only the front wall is there. So, from the front wall it will be reflected back. Okay. Let us see this picture. I creating a sound here and there is a reflector. Okay. Now, distance between the source and measurement point is nothing but a dm, and distance between the source of that obstacle is ds. Then refracted sound reflection path is it going from here, go to ds and reflected back from ds. So, let us normal incident. So, distance is reflected distance is 2 ds plus dm plus dm. Similarly, if it is arranged like this way, then it is nothing but a this is the direct sound and reflection is going that and coming by that. So, it is nothing but a 2 dms plus dm reflected sound path. Okay. Now, you know that what is the reflected power, reflected sound pressure level, measurement point you know divided dm. So, it is direct sound power divided by the distance plus direct sound. So, if the direct sound I measured at the measurement point 10 dB, so it will be 10 plus 20 log dm by 2 ds plus that. Now, if I say I produce 10 dB, but once it is reflected from the wall absorbs some part. So, the absorption coefficient is A. So, 1 minus A is reflected. If the absorption coefficient is A, let us 2% is absorbed. That means 92% will be reflected, or let reflection coefficient 0.2, then 1 minus 0.2. So, 0.8% of the energy will be reflected. So, 10 log 1 minus A will be the actual sound pressure level of the reflected sound. Okay. So, that way we can measure. Then what is the time? There is another things. What is the direct sound time is nothing but a dm by c in case of first case. Reflected sound is nothing but a 2 ds plus dm divided by C. So, what is the time difference between the reflected sound and direct sound? Minus dm by C, I can say, okay, or it is 2 ds by nothing but a 2 ds by C. So, that is time we will discuss what is the effect of that time delay for a room enclosure, all these things will be discussed. Okay. So, this is a reflected sound delay. Okay. Now, there will be another things. Once a acoustic environment, when I talk about the acoustic environment, I said that if I produce a sound in an environment, it create an acoustic environment, and some parameter like atmospheric absorption, reflection, refraction, temperature gradient, all ground surface, all create a some effect on that atmospheric acoustics environment. Ambient noise also create an acoustics environment. Now, if I say that I produce a sound in here, that means it create a sound field, you know that. If I pass a electric signal on a cable, it create a electric field. Similarly, if I produce a sound here, it create a sound field. Okay. So, this whole environment is called sound field. Now, that sound field has different kinds of variation. First one is called free field. What is free field? Free field means that sound only travel, there is no reflection back from any surface. So, this is called free field. So, a sound field is said to be a free field if it is uniform, free of boundary and is undisturbed by other source of sound. In practice, it is a field in which effect of the boundary are negligible over the region of interest. That means, if I say I create a sound here and after a long distance there is a wall, sorry. So, that wall may not, there is a reflection, but reflection energy in here may be very small. So, I can say up to here and here is a free field, because there is no reflection kind of things, there is no extra sound source also. So, only the source sound is propagated based on the inverse square law principle. That means, doubling the distance 6 dB down intensity. Okay. So, in that case I can say it is a free field. Example, real life example, anechoic chamber. If you visited any microwave lab, there may be an anechoic chamber, that means there is no reflection of microwave frequency. Similarly, I can make an anechoic chamber of the sound, that means I can make a chamber where no reflection from anywhere, that means there is no reflection sound. So, only one directional source sound is there. So, that is that room sound is called free field. Okay. Now, there is another field is called diffuse field or reverberant field. A diffuse or reverberant field is one in which the time average of the mean square sound pressure is same everywhere and flow of energy in all direction is equal probable. That is the definition. In practical, what is? Suppose I create an enclosure and this enclosure all 6 walls, all 6 planes are made of a completely reflective surface. There is no absorption. So, that means, if I produce a sound, sound will be reflected back, sound will be reflected back, sound will be reflected back, sound will be reflected back. So, all from all point sound will be reflected back. Okay. In that case, if in a reverberant sound field in which the time average of the mean square sound pressure in the same in everywhere, that means, if I take the mean square sound pressure level this point and take the sound pressure level is this point, which will be reflected on different path, and this point, this point, this point, this point, all point measurement will be same. That means, in all direction equal reflection is happened and total number of reflection produced reflected signal creating that energy and direct sound total energy will be same in every point of the room. Because if it is direct sound, it is reflected, since the reflection path is less, then direct sound may be less, but since the reflection sound will be high, so it is compensated. So, in that case I can say if it is a completely reflective enclosure room and if it is create a sound and in every point of that room the RMS sound pressure level is same, then we said this sound field is nothing but a diffuse or reverberant sound field. Now, you know that reflection is two type. What diffuse? What do you mean by diffuse? If it is a regular reflection, then what will happen? The sound source will be directional. It makes the sound source directional. That means only this square, there will be no reflection on that. Scatter reflection will be not there. So that's why I want a irregular reflection, so that everywhere the number of reflection sound mean or average number of reflection sound will be same. We will discuss later on also this one. So that's why it is called diffuse field or reflective field. Then there is a called semi reverberant field. Okay, can you give an example of a reflective field, reverberant sound field? Real life example. When we entered in a bathroom, all the walls are glazed style and ceiling also not that high. If you create any sound on the bathroom, it create an reflection and create a sound field which is almost diffuse or reverberant sound field. Okay. Now, I go for the another sound field which is called semi reverberant sound field. What is semi reverberant sound field? The semi reverberant sound field is that where only one parameter I relax, that okay, all the wall, all the surface which is there is a some portion of the sound is absorbed by the surface. That is not completely reflective surface, some absorption is there, then it is called semi reverberant sound field. So, in case of semi reverberant sound field, may not be all point the power energy will be the same, okay, and in flow of energy is more than one direction. Okay. Now, there is another sound field which is called pressure field. A pressure field is one in which the instantaneous pressure is everywhere uniform. If a sound field is like that instantaneous pressure in sound pressure in everywhere is same. Instantaneous sound pressure in everywhere is same, then we call is a pressure sound field. This is used for microphone calibration. Microphone calibration, we use this kind of uniform pressure sound field. Then there is a, depending on the position of the field, there are two types. One is called near field, another is called far field. What is near field? If you remember, when I discussed about the spherical wave propagation, I said that if the frequency of the sound or if the distance from the source r is comparable with the wave number or wavelength of the sound, wavelength of the produced sound, then the theta, cos theta, have you remember the cos theta? Theta is the angle between the pressure and particle velocity p and u, that angle theta will be large, So, in that region, when the theta is large, in that region it does not follow the inverse square law. Okay. So, the region from the source to the region where the sound energy or sound propagation does not follow the inverse square law, or the region which is the distance from the source is so small compared to wavelength, the theta is high, the angle between the pressure and particle velocity is high. In that region, inverse square law does not support, that region is called near field. So, it is near to the source, that is why it is called near field. So, what is far field? Far field is that where the near field is end, the far field is start and it goes up to infinite. Okay. So, that is called far field. Okay. Now, I just given one picture. If you see Let's this is the sound source I taken from internet, that so up to here if you see the near field, let up to here it does not follow the inverse square law, then I call this is a near field, this portion is the near field, and far field is the end of the near field to the infinity is the far field. Okay. Now, if you see interesting observation that I said the wall is here. So, there is a reflection, but in here this region there is a reflection energy very low. So, I can say the only the direct sound exists in here. So, this is called free field region, only direct sound, and this end let us here up to here the no reflection sound is not there. Once the reflection sound start, we call reverberant field. So, three field: near the speaker, near field, after the near field, far field is started. In far field, two type of field, one is called free field, another is called reverberant field. Okay. So, I can explain, I can discuss that how depending on the placement of the speaker, I can calculate which is near field, which is far field, and which is reverberant field. Okay. This will be used when we design the auditorium. Okay. Now, there is another point is called ambient noise field. Suppose I produce I giving lectures and there is a AC and it creates a constant noise. So, it is an ambient noise. Or suppose there is a concert in in open air let us say in our OAT open air theatre, and beside that there is a road. So, when the car is going on the road, it creates a noise. So, it is ambient noise is created. So, that is called ambient noise. So, ambient noise is also affect the sound field. For example, suppose I told you that I create the ambient noise level in a field. I want to set up a concert in our Gyan Ghosh Stadium, which is a free, means in Gyan Ghosh or Tata Steel Sports Mart. So, what is that? I have put some loudspeaker, and I said that when the loudspeaker is not on, the average ambient noise is 70 dB. Okay. Now, I switch on the loudspeaker, and after 4 feet I measured that it is produce 110 dB sound. Then can I calculate how far the sound will be travel before it submerged with noise? That means, in up to which distance audience can hear the sound? Okay, I can calculate, because I said that let us forget about the ambient absorption by the noise atmosphere and absorption by the people who are standing there and the noise created by them. So, that also create the ambient noise. Let us people standing on there and their created noise when the loudspeaker is not on is 70 dB. Okay. Now, let us atmospheric absorption is not there, wind is not, wind blowing is create some help or distract. So, it create an effect, but let us it is not there. Then what will happen after 4 feet, if it is 110 dB, then it is ambient noise is 70 dB, then I can easily calculate how far the sound will be travel. So, it will be around 400 feet, the 400 feet sound will travel. So, I can calculate how far the sound will travel, and then after that distance I put in another speaker, so that sound can travel long distance. So, it helps me to calculate where I put a loudspeaker in that region. Now, if you see the picture, this is a sound source, it creates a field and the different kind of noise is there. Okay. Now, in acoustic open air or outdoor acoustics, you found that there is a stage, this kind of stage is there. Once I put a stage, this kind of stage, the sound is directed. So, in this direction sound will be enhanced, because this direction sound will be reflected back on this region. Okay. Similarly, if I see that instead of if I make the stage like this and put the audience in a RAM, then what will happen? The sound will be again enhanced. or air, if it is sound is going upward also, this can help to travel the sound in long distance. So, this kind of outdoor acoustic arrangement we made. If you go to the open air theatre OAT, you see the seats are ramped. It is not only for viewing, it is also for sound, that every people can hear it clearly. We will thoroughly discuss when we design the auditorium. Okay. So, this is called acoustics environment. Okay.